Welcome back. We just figured out we can calculate rates. We can say, hey, if I've got this table of data versus time, I can calculate rates at the beginning, I can calculate rates over certain time intervals, and we'll get some chances to do that in lab. So you'll have a chance to actually calculate some rates and do that kind of work in lab. So what we want to know is, how exactly do we know? Because we're trying to figure out this following reaction. We've got the blue dots and we've got the purple squares. How do we know exactly how that rate depends on those concentrations? When we said in the past, a whole couple videos ago, we said that the rate was going to be proportional to our concentration of blue times our concentration of purple, or equal to K times the concentration of blue times the concentration of purple. But that really was just an assumption. We were just kind of talking out loud and reasoning it out. We didn't have a way of knowing for sure that it's always going to be equal to those two things multiplied by each other. And it turns out that that was just an assumption. It's not actually the way we're going to be able to figure this out. So we're going to compare this. We're going to compare to the reaction NO2 plus F2 goes to 2NO2F. Now, I'm going to break this off. There's two NO2s. I'm going to draw one of them in green. So I've got NO2 gas. And I'm going to draw the other one in blue, NO2 gas. And then we've got F2 gas goes to 2NO2F. And that's also gaseous. And what we're going to say is, well, if we do that same logic we had up top, we said that our rate is going to be proportional to the different things that are in there. The reason I use two different colors is because there's two different NO2s that we're having to consider. We're considering the green NO2 and we're considering the blue NO2. And if we're saying these three things have to come together at the same time, then it's going to be dependent on how many green NO2s we have and how many blue NO2s we have. Might not quite make sense to you because you're like, they're both NO2. But if we need two of them, we need to distinguish, because we can't just have F2 and NO2 coming together. We have to have F2, NO2, and another NO2 coming together, right? And that's how we're going to distinguish these two NO2s, this one and this one, a green one and a blue one. So here I might say that my rate is going to be proportional to green NO2 concentration, blue NO2 concentration, and F2 concentration. Now, since it's all in the same beaker, these concentrations, the blue and the green, are going to be equal, right? There really is actually no distinction between the blue and the green ones. And so this would be proportional to NO2 squared times F2, or equal to K times NO2 squared times F2. And that's what we'd get just by thinking through it. And we say, okay, well, so that's how we're going to relate those rates to those concentrations, and we'd be wrong. Because if you actually do the experiment, you don't get that, okay? This is what we'd call a proposed rate law. And we'll define rate law in a little while. But we're going to call this a proposed rate law. But we'd be wrong, because it turns out you cannot. It is absolutely impossible to just look at a balanced overall chemical reaction and decide what the rate law is. We can make guesses, and we might be right, we might be wrong, but it's actually impossible to figure it out just by looking at an overall reaction. We can figure out all sorts of things from overall reactions. We can figure out stoichiometry, we can figure out enthalpy, all sorts of things. But kinetics and rate are not one of them. So, how are we actually going to figure out how the rate of these things depends on the concentrations of NO2 and F2? And it turns out there's only one way. The way is you have to do experiments. You actually have to run this reaction in the lab, record things, analyze that data in order to figure out how the rate depends on NO2 and how the rate depends on F2. We do know a few things, and that the rate is only going to depend on reactants. So we only depend on our reactants. We're not going to depend on our products. Okay, so we only depend on reactants. And in some cases, towards the end of this chapter, we're going to say, hey, there's going to be catalysts there as well. But catalysts can actually be part of your reactants. So only dependent on reactants. But how is it? So if we actually look at this one, if you do the experiments, the actual rate law is going to be that rate is equal to K times concentration of NO2 to the first power times F2, not to the second power. It doesn't depend on both of those hitting, it just depends on one of them. And that's not really intuitive to what we were doing before. But that's what the experiments tell us, and the experiments are the only way to know. Okay? So what can we say about the rate laws? If we have our generic reaction, oh gosh, our generic reaction already. We've got AA plus BB goes to CC plus DD. What can we say about that? Well, we can say that the rate is going to be equal to some constant, doesn't matter for now what it is, times the concentration of A and the concentration of B, right? It only depends on the reactants, right? That's what I just said before. But what we don't know is what power. And so we cannot, I'm going to write it wrong first, we cannot just write A there. That's not necessarily true. It's sometimes true, but it's not necessarily true. And so what we do is we put a placeholder. We say M. And M doesn't occur anywhere because we have to figure out what M is. And we can't just write B here. That's not correct. We just write N. Right? So we write A to the M and B to the N. If we had C and D as reactants as well, it would be dependent on those to different numbers that we'd have to figure out. So M and N are usually whole numbers, and they're usually small. Turns out they don't have to be whole numbers. They're almost always small. They don't have to be whole numbers. But usually they're whole numbers and they're small. But the thing to remember is that M is not necessarily equal to A. Sometimes it is, sometimes it isn't. N is not necessarily equal to little b. Sometimes it is, sometimes it isn't. The only way to find M and N is to actually do experiments. Right? This is what we call the rate law. The rate law defines how we can calculate the rate based on concentrations. Now, notice concentrations changing over time, right? We're reacting these things. So this is at any given moment in time. At any given moment in time, if we know that rate constant, and we'll figure out how to calculate that later on, the concentration of A and the concentration of B, and if we know those powers of M and N, we can calculate the rate. Why is it important to know the rate? Well, if you're designing something, you want this reaction to run, you want this thing to happen, you better make sure that your rate is such that it can happen in somebody's lifetime, because if it can't, it's not very useful. Okay? So rate is actually pretty important. So we're going to do that. That is our rate law. It relates rate to concentration at a given moment in time. K is what we call the rate constant. It is the proportionality constant between the concentrations of A and B and the rate. Rate, like I said, is normally measured in units of molar per second. It doesn't have to be. It could be molar per hour. It could even be molality, but most people will use molarity, and they'll use seconds. Okay? And it turns out you can get all sorts of different units for K. We'll take a look at some of them as we go through. So we're going to get all sorts of different units for K, but it is called the rate constant. So this is the rate law, this whole big thing here, the rate law. Everything relates rate to a constant and concentrations at a given time. The rate constant is just this little guy K, and it is that proportionality constant between those concentrations and the rate. It can get a little confusing to keep track of all the language in here, so just do your best to try to learn. Rate law, big thing, concentrations related to rate at a given moment in time. Rate constant, just that value K. All right. Next slide. So we're going to talk about reaction order. We're going to start with a very simple reaction, which is A going to B. And if we have the reaction A going to B, we can say that the rate is equal to negative 1/1 times the concentration of A over T, or we can say it's equal to positive 1/1 change of concentration of B over T. But remember, I said we're going to find lots of different ways of calculating rate, and they're all the same. Right? So this was our definition of rate, right? That was our general case of the definition of rate. But now we know something else. That's equal to K times A to the M. So now we have this way of relating our change in concentration over change in time to concentration at a given moment in time. Whew. It gets a little hard to keep track of, but we will get there. Okay, so our rate that we defined, this is what rate means, is now also represented this other way by a rate law. Okay, so this is always true. Right? There's no situation for the reaction A goes to B where this is not true. Now, we know that m is usually a small integer, right? Small whole number. And so let's say we knew, for example, we know that m is equal to 1. Okay, if m is equal to 1, just as an example, then we've got that the rate is equal to k times the concentration of A to the first power. So we don't have to write the 1 there, but rate equals k times the concentration of A. We call this a first order reaction because it's first order, it's order 1 in A, right? We've got that 1 there that we don't write. It's a first order reaction. On the other hand, let's say for a different example, we somehow knew that m was equal to 2. Then we have that rate is equal to k times A squared. What do you think we call that one? First order reaction A? Yeah, second order reaction. And if m was equal to 3, we'd call it a third order reaction. You're getting good at this. Okay. How about if m is equal to 0? We'd get that rate equals k times A to the 0. Can it be 0? It can be. Okay, so rate equals k times A to the 0. That way, it's just equal to k. Well, that's cool, because then it doesn't depend on the concentration of A, which seems a little counterintuitive. Like, shouldn't a rate depend on how much I have? And in most cases, it does. But in some cases, it doesn't. And we do call this a 0 order reaction. So first order reaction means it is power 1, second order reaction power 2, and 0 order reaction means power 0. But here we're talking very specifically about just A. We're saying, hey, it's first order in A is the language we use. But what if we had a more complicated reaction? What if we had, I don't know, a generic reaction, oops, I wanted a different color. What if we had a generic reaction, A plus B goes to C plus D, our favorite generic reaction? We know that the rate is equal to K times the concentration of A to the M, the concentration of B to the N, and then we have to figure out experimentally M and N. Let's just do some examples. Example, M equals 1, N equals 1. We'd get that the rate is K times the concentration of A to the first times the concentration of B to the first. And here's the language we use. We say this rate law, right? The entire thing is the rate law, tells us that the reaction is first order in A. That's the language we use. We say it's first order in A. We also know that the reaction is first order in B. And then we have something we call the overall order. And it's just the sum of the orders. In this case, it's going to be m plus n equals 1 plus 1 equals 2. And the overall order, we say it is second order overall. So this reaction is first order in A, first order in B, and second order overall. So that's an example. What about a different example? What if we happen to know that m equals 2 and n equals 1? Well, then we'd say that the rate is equal to k times the concentration of A squared times the concentration of B first. And we'd say this reaction is second order in A This reaction is first order in B, and the reaction is third order overall, because 2 plus 1 is 3. So that's the language that you're going to hear people use, especially saying this reaction is first order in A, this reaction is second order in B. You're going to hear that kind of language very, very frequently. The overall order you do hear occasionally, so you need to be familiar with it, but certainly saying first order in this, second order in this is much more common. And yes, it can be third order in something, it can be zero order in something, and we're going to use that quite a lot. All right, let's do some specific examples and see if we can see some things we can learn from these rate laws. So we've got a reaction. It's got a rate law of K times the concentration of A. So we call that a first order reaction in A. We know that when the concentration of A is 1.0 molar, the rate of the reaction is 2.0 molar per second. What I want you to do is figure out the value and the units of the rate constant K. Go. All right, what did you come up with? Well, hopefully you just started plugging into this. You said that my rate is equal to K times the concentration of A, and my rate was 2.0 molar per second equals to K times my concentration was 1.0 molar. I'm going to go ahead and divide both sides by 1.0 molar. And it cancels out 1.0 molar on this side. The molars cancel out on this side, right? I don't know what happens when your molars cancel out. I guess you chew lettuce. Okay. So K is equal to a value of 2.0. What's our unit left? Well, it's only over seconds, right? We have no unit in the numerator. So you can write K is 2.0 per second. You can also write K is 2.0 seconds to the minus 1. Those two are an equivalent way of writing it. So we got C in this case, that K was 2.0 per second. All right, so that's how we can calculate our K values by knowing some rates and some concentrations and orders of reaction. And you notice K kind of has this fun unit. What is per second? You know, it's hertz, right? It's cycles, but it turns out it doesn't really mean much. The units of K are actually unimportant from a meaning standpoint, very important from a utility standpoint. You have to have K with the right units in order to get the right units for your rate. Next one, a reaction has a rate law of K times the concentration of A. It's first order in A. When A is 1 molar, the rate of the reaction is 2.0 molar per second, exactly the same as the last one. So we determined that K was 2.0 per second. And what is the rate of the reaction when A is 2.0 molar, right? When you double the concentration? Well, it turns out that's pretty easy to do. We could say that the rate is equal to K times the concentration of A. Oh, I forgot to give you a moment to do it. Silly me. Go for it. Okay, so now you can say the rate equals K times the concentration of A. We can plug in. We know that K is 2.0 per second, and we know that the concentration A is 2.0 molar. And when you do that, you get 4.0 molar per second, and you get answer E down here. So what happened? When we doubled the rate, the concentration of A, we doubled the rate of reaction. And that makes sense, right? If you take this equation and say the concentration of A times a constant is equal to the rate, if I double A, I should also double my rate. What would happen if I tripled A? I should triple my rate. If I quadrupled A, I should quadruple my rate. What if I took A down by a factor of half? I said, hey, I've got half as much. If I had, instead of 1.0 molar A, I had 0.5 molar A. I should go down by a factor of half on my rate as well. That's a generic thing. Well, let's step it up a notch. What if we have a rate law of K equals A squared times B? When A is 1 and B is 1 molar, the rate of the reaction is 2.0 molar per second. What is the value and units of the rate constant K? Your turn. Okay, what'd you come up with? Well, plug and play, folks, plug and play. So we've got rate equals K times A squared times B. And we're given all that information. 2.0 molar per second is equal to K times A squared, 1.0 molar squared times 1.0 molar. Right? So what do we end up with? On the right, we end up with K molar cubed. What is a cubic molar? I have no idea. Nobody has any idea. The meaning of these units doesn't matter so much. The actual getting of them does matter because it's important for getting the value our rate correct. So I've got 2.0 molar per second times k molar cubed, right? I don't have a number there because it's just 1. I'm going to divide both sides by molar cubed, and I get 2.0 per molar squared second. Whew. So I get C again. 2.0 per molar squared second. You could also write that out as 2.0 molar to the minus 2 second to the minus 1, right? Because those minuses just mean 1 over. So either way you want to write it is just fine. You'll see it both ways. Some people like the fractional way, some people like the exponent way, and either way is fine in my world. So 2.0 per molar square second. What is a molar square second? I have no idea. No one does. It's okay. But you need those units in order to get the proper unit for your rate. Same thing. Rate k, a squared times b. A is 1, b is 1, 2.0 molar per second. We determined in the last slide that k was 2.0 per molar square second. And what is the rate of reaction when A is 2.0 molar, when the concentration of A is doubled? All right, what did you come up with? Well, the rate is equal to k, a squared b. Yep, so we've got a squared b. That's going to be k, well, we've got k, 2.0 per molar squared second. A is 2.0 molar squared, right? You have to square the whole thing, square the concentration of A. And B is 1.0 molar still, because it didn't show us as changed. And what we have 2.0 per molar squared times 4.0 molar squared times 1.0 molar. 2 times 4 is 8, 8.0 molar cubed on top, molar squared on the second, 8.0 molar. Oops, I forgot my seconds there. I'm like, I'm missing something. 8.0 molar per second is my rate. And so I get D in this case, 8.0 molar per second. So when I doubled the concentration of A, what happened to my rate? Well, it went from 2 to 8. It didn't just double. It went 4 times. Well, what is 4 times? 4 times is 2 squared, right? I took what I did, I doubled it, and I squared it because that's what I do with the concentration of A. So it works out with numbers all the time. You can always plug in numbers and figure these things out. But it turns out we can think about it logically too. So I'm going to write this guy down here again. Rate is equal to k times a squared times b. I'm going to say, hey, what would happen to my rate if I double the concentration of B and hold A constant? You're like, I don't know. I don't have any numbers. Well, we can figure it out, right? Since B is first order, if I all of a sudden put 2B in there, right, 2B or not to be, yes, I want to put 2B in there, right? That's just going to be in parentheses. And that 2 is just going to travel over here, and we're going to get 2 times k a squared b. Right? So we get 2 times our original rate. And so when we double b, we get double the rate. On the other hand, if I put a half in there, if we get half as much b, what am I going to get? I'm going to get half as much rate. What about, so this was if I double b. What about if I triple a, right? Not the kind where you call because your car is pulled, broken down on the side of the road, but I'm going to triple my concentration of A. So let me put the concentrations there. What do I have? I have rate equals k times a squared times b. And my new A is actually just 3a, right? So it's k 3a squared b. Well, right? 3a squared is going to be 9a squared, right? So this is going to be k times 9 times concentration of A squared times B. I'm going to move that 9 all the way to the front, and I get 9 times k A squared B. Hey, look, k times A squared B, that was my initial rate. Right? Woo, that was my initial rate. So what do I have? I have 9 times. So by tripling A, because A is squared, I now have 9 times the rate. Whew, This is kind of fun, actually. How about if I do something a little more complicated? What about if I take b in half and a 4 times? Ooh. Do the same way. Rate is equal to k times a squared times b. My new a is 4 times what it was. My new b is half of what it was. And so I get k, 4 times 4 is 16 times 0.5 b. I move things up to the front. I get 16 times 0.5 times k a squared b. Look, that is my initial rate. And so what do I have? I have 16 times 0.5 that. I have 8 times my initial rate. Okay, so when I take b in half and a 4 times, I get 8 times the rate. And you actually don't have to do it this long way. You can actually do it kind of a shorthand way, which just says I've got rate equals k a squared b. And let's say I take a in half and b 3 times. What you can actually do instead of doing all that work up there, but that's kind of how it works, is I say, let me just put those numbers in. I get k and I get half, 1/2 squared, and b, I get 3. So what is that? That's going to be 1/4 times 3, which is 3/4. So if I took a in half and b 3 times, I actually get 3/4 of my initial rate. The work up there is how it works out, but you can do this kind of shorthand and think about it that way. It'll be useful to be able to do this kind of stuff in your head when we're talking about one of the ways of using data in order to get a rate law. So that was our foray into exploring rate laws and how we can use them to find values for k, how we can kind of change some things and figure out how our rate changes, and just about reaction order in general. What we're going to do next is we're going to say, how do we take experimental data and turn it into a rate law? Thanks for listening.